Welcome to Lecture 8. Today, we are looking at emerging and converging technologies, an area of study that defines the modern computing landscape for UUM School of Computing students. Historically, computer science focused on the engineering of isolated systems. You built a discrete software or hardware, and it operated independently within a defined boundary. This illustrates technological convergence. Distinct domains like AI, IoT, and cloud computing interconnecting into a unified architecture. The modern smartphone exemplifies this, combining sensors, telemetry, and AI. Increased complexity at every intersection introduces specific challenges in surveillance and data concentration. When a system's impact moves beyond a single device or predictable environment, traditional computing ethics encounter scenarios they weren't designed to handle. To understand these risks, we have to trace where convergence is happening. The first layer is the environment, where the user's physical surroundings become the computing interface. This is ubiquitous computing, the embedding of microprocessors and sensors into the fabric of daily life, from wearable devices to the infrastructure of smart cities. These environments are powered by ambient intelligence, or AMI. Unlike legacy sensors, AMI systems actively process and respond to human presence in real time. Take smart home surveillance systems. For the hardware to anticipate a user's needs, the microphones and lenses must be active and collecting data continuously. This reveals a strict architectural trade-off. Achieving a seamless, frictionless user experience requires continuous environmental monitoring. The direct ethical consequence is an erosion of privacy. The system design demands perpetual data harvesting to maintain functionality. When the physical environment itself becomes the computer, opting out of data collection becomes a physical impossibility. Moving inward from the environment, convergence reaches the human body. This demonstrates bioinformatics, the convergence of biology, data science, and computing to digitize human code. Converting biology into a data structure allows massive scale in genetic analysis and medical research. However, as private companies store sequenced user DNA, ambiguity over data ownership emerges. Corporate ownership of genetic data generates the systemic risk of misuse, unauthorized distribution, and third-party monetization. This data can be weaponized into deterministic bias. Genetic discrimination occurs when health insurance or employment decisions are based on statistical probabilities found in sequenced DNA. A compromised computer password can be reset. A breach or misuse of biometric and genetic data is permanent. The architecture offers no reset button for your DNA. Digging deeper, we reach the microscopic hardware layer that interacts with these biometric systems. Nanotechnology is the engineering of functional systems at the molecular or atomic scale. Operating at this size enables nanocomputing, microscopic electronics, and internal medical telemetry. The ethical concern here stems from an information deficit. We face unknowns regarding the long-term effects of synthetic nanomaterials on human biology and broader ecological systems. This creates an architectural blind spot. There is a lack of regulatory frameworks capable of testing, tracking, and monitoring technology that cannot be seen. Deploying hardware at the nanoscale introduces the risk of irreversible environmental and biological integration. It is a hardware deployment that a software patch cannot fix. Pulling back from the microscopic scale to the macro level, convergence reaches the point of physical action. System architecture is shifting. Artificial intelligence is moving from advising human operators to acting independently as autonomous systems, driving cars and operating robotics. This transition requires machine ethics, a specific engineering discipline dedicated to mathematically constraining autonomous behavior. This fault tree diagram outlines a known scenario, a self-driving car facing an unavoidable crash, forcing a choice between two harmful outcomes. Engineers treat this as an algorithmic weighting problem, programmed to execute the pathway with the lowest assigned negative value. But when the system executes a harmful action, liability becomes diffuse. Does accountability lie with the programmer, the end user, or the algorithm itself? This is your class activity discussion case. Should autonomous AI systems be allowed to make life and death decisions? Delegating high-stakes physical decisions to converged autonomous systems creates a gap where legacy liability and accountability models lack clear application. Traditional tech ethics rely on static, reactive checklists that are completed and filed away before a product ships. Converged technologies, ambient intelligence, bioinformatics, nanotech, and autonomous systems are non-deterministic. They evolve after deployment, making a static checklist obsolete. The required solution is a dynamic framework designed to evolve alongside technology. Step 1. Continuously identify new risks. Step 2. Analyze ethical impact, integrating law, sociology, and engineering. Step 3. Actively update policies. Step 4. Monitor the system post-deployment, feeding data back to Step 1. Your professional practice involves engineering physical environments, digitizing human biology, and building autonomous agents. To succeed in the era of convergence, your architectural frameworks must be engineered to be as ethically resilient as they are computationally efficient.